So thank you everyone for coming for today's session of the bi-level optimization webinar. So this is the a second last session of this season. We have another one, but today we have Didier. Thank you for coming up to this webinar today. So he's a mathematician, professional, passionate by applied mathematics, and more specifically by optimization. He started his research life focusing on theoretical aspect of optimization, and step by step completed his research field panel by more and more application of optimization, energy markets, demand-side management, isolated energy system, circular economy, etc. And sometimes he reached to what he calls applicable mathematics that are for him mathematical theory that aim to be as close as possible to the real world. His research laboratory is Prom Lab in Perpignan, France, but his research network is the world. Indeed, he used to collaborate with colleagues from many places on the planet: Australia, Brazil, Canada, Chile, Cuba, Czech Republic, and so on, and sometimes from France. And the collaboration and sharing without border is his guideline in his research. I really love his your bio, Didier, and thank you for accepting our invitation. And
No.
the floor is yours.
Thank you for the introduction. Yeah, indeed, I'm of course still because I started like that, be interested by theoretical results, which mean existence result, for example, in Banach spaces and stuff like that with abstract object. But at some point, I also like to have what I call applicable math, which means modelizations that are quite close to reality, using real data and trying to, well, to bring the math models and the work we do to the scale of society and to the scale of human needs. So some of the part of my talk today will be like that. Some of the one will be more theoretical. It will be a mixture. So let me share my screen. Yeah, this. Let's go. I guess. What is this here? By the way, I guess I have too many slides and too many things to say, but anyway, they will stop me when I will be too long.
I can remark like 15 minutes before. I can also remark as well.
Yeah. Do not hesitate. Do not hesitate. Yeah. Because actually, I was a bit puzzled when constructing this presentation because I wanted on one side to present an alternative approach to the Nash modelization on one side, and on the other hand, I wanted also to how to say, to speak about the well-posedness of the single leader multi-follower or multi-leader multi-follower games in general. So I did a kind of compromise. Actually, in the abstract, I promised to work on 3 different models alternative to Nash. Finally, I will tackle only 2, but I will speak a bit about well-posedness. I guess it is very important. And looking to some of the talks that I saw in Edinburgh last week, people having some models which are not extremely ill-posed. I think it is always important to recall a bit about well-posedness of those difficult problems. So you confirm to me that you can see my screen, right?
Yes, it's perfect. Thank you.
Okay, very good. So let's start. So, yeah. So first, I am a prof in applied math at University of Perpignan, and University of Perpignan is there at the south of France. And actually, mainly my topics are, of course, bilevel optimization, Nash, and multi-leader follow again, but also application to energy market, industrial eco parks. I will speak a bit about that today. Demand-side management, which is very important nowadays for the management of energy, and many other applications, but also variational and quasi-variational inequality and quasi-convex optimization. So you will see that actually all those topics will appear in this talk at some points. And I have the chance actually to be member of a research lab, which is a lab of energy. It's not a lab of math, it's a lab of energy, which provide me with some very interesting opportunities to interact with people from energy, understanding their concerns, their problem, and exchanging with them on the new development. So what I will present today essentially is a bit about multi-leader following games, a bit of vocabulary, about well-posedness, and a bit of the classic setting, I would say, which is Nash. And then I will forget about Nash and go to different other alternative modeling, which is, to my opinion, a very exciting open field where a lot of open questions are present. So, well, just, I mean, I will not insult all of you by recalling basic things, but I would like just to fix a bit of the notation concerning the GNAP. So, of course, GNAP is a package of people that will interact in a supposed non-cooperative way. They have their decision, each of them xi, and there are the decision of the other one, x minus I. And of course, the set of decision of one guy, xi, is in a set which is which depend of the decision of the other one. Okay, so we know this perfectly, and which means that nobody has the advantage to unilaterally deviate. I will come back to this. I included this slide because I will come back to this at the end of my talk by considering an alternative to that, a stronger alternative to that, that goes a bit further. Anyway, so yeah, and so of course, one other way to present this is to consider the response map. So there are set valued maps, of course, and then X bar is a GNAP, if and only if it is actually in the product of the response function or the response map, set value maps. And a very simple example is this one, for example, where for this you have the response being Y2, for this being 1, and thus the GNAP will be 1. Okay. But now, when you have this in hand, this model, it is important to know under which condition it exists. So after the pioneering work of Arrow, De Breu, and those famous guys, a lot of improvement has been done in this direction concerning equilibrium. I will not develop this here today, but there are plenty of new results that have been developed, weakening assumptions or giving some alternative hypotheses. And also, of course, what kind of first order condition you can use. So I'm not speaking about KKT, which is a very classical one. You write the KKT of each of them, or each of the problem in terms of the decision variable, and you concatenate, and then you solve this problem. This is not what I would like to speak about, but more about more general setting where you don't have, for example, the differentiability of the utility function or the constraint or whatever. And also associated to that, of course, qualification condition for the reformulation to be equivalent. And this is, by the way, quite neglected, and it is very important point to spend a bit of time each time we reformulate and to see under which qualification condition we have this reformulation. And now, of course, we mixed this with bilevel optimization, for which the same, I would say, main topics has to be developed. So existence, of course, first order condition, again, possibly with non-differentiability, and qualification condition. So of course, if you have some differentiability, so say here you have some differentiability of phi and the inequalities or equalities defining the y, then you can write a KKT, and it is well known that then you obtain an MPCC, and qualification condition for that to be equivalent have been studied. And for the moment, the most efficient ones, or I would say the most weakest one, is a GINAR qualification condition. But you can consider other kind of setting, and in particular, we in our modelization, you will see that we don't use derivative. Okay, and that's when you mix this and that is a GNAP And Bilevel, what do you obtain in a classical way? You can obtain single leader, multi-follower game if you have only one leader and several followers competing in a Nash situation. Or, of course, you can have multi-leader, single follower games with the leaders competing between them in a Nash game and having the dependence on the decision of a follower. And of course, you can have the most general setting, which is a multi-multi, where you have a Nash at the top and the Nash at the lower level. And if you have a look to the title of my slide here, it is there are multi are problem where I don't want to go for the moment. And there is very deep reason why I don't want to go for the moment. It is because actually those problems, they are extremely ill posed. Extremely ill posed. There are a huge difficulty in the formalization of that. I could deliver a webinar just on that. There are so many things to say that I could deliver a webinar just on that. But since I wanted to go further into non-Nash modelization, I advise those that are interested to contact me at this email address, and I can send to them a series of slides extracted from some schools that I delivered, in which I give some element of ambiguities in the multi-multi setting. Please trust me, before going to multi-multi, be very cautious. There are plenty of big ambiguities. Okay, so now I will concentrate for the rest of the talk on single leader multi-follower game. We'll speak about a bit of vocabulary. We'll speak about the relation between leader and follower and who we are, and actually what is a natural way to model this. And then after that, we'll go to single leader multi-follower game where you don't have Nash. So what's happened here is that when you have a kind of modeling like that, you can have actually here a constraint, say an inequality here, which link X and Y, and this is kind of selection of the Nash. It's like if you actually say first, so you give X to the followers, there is a Nash determined or several Nash, and in between the several Nash, you select the one passing this test of satisfying this the share constraint, so which is called coupling constraint, coupling constraint. And this is kind of selection a posteriori of the GNAP. But of course, you can have also situation where actually you have situation like that here that are constrained just depending on the decision of the player and the decision here of the follower. Then actually it's just a Nash in this case. But you can have also what is called here share constraint. That is a constraint which is shared by everybody, the same one. Say, for example, the sum of the goods that are on the market are, the sum of the goods that people will buy on the market is less than what is available on the market, simply this, and this kind of inequality. And this is common for everybody. So at this position, if you put this constraint at this position, then it is called the share constraint. Actually, moving this kind of thing here from this level, share constraint, to this top level here, so changing them into coupling constraint. This is a work that we are currently exploring. I mean, we are exploring this interrelation between those two reformulation with Martin. So you will soon have some result on that. Yeah. But I would like just to speak a bit about well-posedness here. So, and ambiguities, even for the single leader, multi-follower. So when you have, say, a single, just a single, then you can observe that from the very beginning, I say mean in quote, because of course, what can happen is that if you have several Y here being answer response of the unique follower here, then you have to choose one because here the value of F can change. So as everybody know, you can, well, example to that showing that there are some ambiguities are very simple. This is one of the example. In this case, for example, you have, if x is negative, then you have only one element as a response. If x is positive, you have -1. But if x is 0, then you have the full line, which is kind of problematic if you want to reformulate, because then the solution function will be here. And what's mean to have a solution, then you have to precise. So a classical situation, so means that this like that. And I can tell you that still today, many papers don't precise here what they take. And that is a very, very bad formulation, which means that I'm not just speaking about, well, theoretical problem. It is, if you go to current papers on Bilevel, you can still have some people not precising what they have, even if they don't have any, I would say, guarantee of uniqueness of the response. So that is problematic. So one of the well-known answer is, well, if I have uniqueness, then very good. I plug this response, which is a function, into my problem, leader problem, and then it is unique level. So it's extremely simple, especially if I have an explicit formula. But even if I don't have an explicit formula, that is kind of coherent. So those are conditions ensuring the uniqueness, of course. And another way, and I would say the most classical way, is, of course, the optimistic, where you say, okay, actually, this follower will help me to reach my minimum. This is why it's called optimistic, because it is considered like the follower is a friend of the leader and try to help him reaching his target, which is to minimize capital F. And of course, you have the pessimistic one, which considers that the follower is your enemy, and you are kind of risk averse, and you don't want to take any risk. And then it is a min-max formulation. But there are also, those are very well known, those two, optimistic, pessimistic, but there are also other formulations. You can, for example, have a selection type. And if you have a look to the electricity market, for example, not modelization, but the functioning every day of the electricity market between France, Germany, Austria, and Switzerland, there is a software which is called Cosmo, solving this clearing problem every year, every day, between 12 and 12:40. And it is of selection type, by the way, because if you have several prices, for example, or several combination of say prices, let's say about the prices, then there is a selection declared into the process to select a given price into the interval of possible prices. So, I mean, it's not just theory, it is practical application. So also you have some selection type way to have a well-posed single leader multi-follower. But you have also some probabilistic approaches, for example. So recently, Sala and Svensson from Chile, they proposed, they proposed, I will not speak so much about that, but a kind of Bayesian approach to select one point into the possible multiplicity of the response of the follower. So those are some kind of very important things that we have to decide before going into the model. But there is also another very important point, and there are not so many people speaking about that. It is, what is a solution, finally? What do we mean by solution? Because, of course, when you consider optimistic, you have this kind of formulation, but you can also rewrite this by considering the value function, which is simply, even if you have multiplicity of y, okay, given x, you have multiplicity of y, then you can have a value function like that, and you say, okay, then I minimize on x the value function of x. And people consider that it is a kind of equivalent reformulation. But of course, it's not. It's not, and why? Because, and for pessimistic, of course, you can do the same by considering the value function with the max. Why it is not? Why there are kind of different approaches, and they are actually adapted. Each of them is adapted to a certain kind of modelization, a certain kind of practical situation, because we need to know what is the solution. So we have the choice between essentially looking for X. I am the leader. I just want to know X and to decide about X, and this is finished. I don't care about the Y. That's simply I need Y to exist, but I don't care about the value of Y. And there are also other problems where you need deeply X and Y together. So you need a couple, and this couple is very important for you to design something. So typically here you are in a market, you are a leader of a market, and you have to decide about the price for a given product. And you have a model for the reaction of the other ones. Okay, very good. But the reaction of the other one will simply give you the amount of the market that you will catch if you give this price or the other X other price. But actually, you don't care about the reaction. You just care about the X, the final price that optimizes your function. And you are happy with that. But imagine that you are now designing something, and you will see an example with the industrial eco park. You are designing something, I mean, putting tubes, putting physical things. Then sometimes, and it will be the case in the eco park design, optimal design, then we need X and Y at the same time, which means that from an application point of view, having this kind of modelization or having this kind of modelization are targeting different aims and different objectives in the bilevel optimization. So with one or several followers, it is the same. I mean, this is the same problem. Because finally, in real life, what happened? People say the stories, this is very funny, very pleasant. The leader play first and the follower react. Of course, it is not true. In real life, what happened is that so those are the two different situations, X and Y. Then I call it optimal design of interaction mode, and just X, then it is a leader strategic process. Those are the names that I created for having a need of just X or having a need of X and Y. But actually, in real life, what's happened is that step 0, the leader has a model of the follower reaction, and then he computes a solution X or a solution XY, and he play finally X or XY or X essentially. But finally, the follower, they will do whatever they want, and they will decide about. They think about the market, you decide about the price, and then you have a model of reaction of the other one. But finally, in real life, this is just a model of reaction, and in practice, people will do another thing. So that is important to have in mind, and just to know if you want X in your practical model, or if you want a couple X and Y. So if you are in the optimal design of interaction mode, X and Y, or if you are in the leader strategic process, just X. Okay. Okay. Now, yeah, this is about the position of the coupling constraint. I will not say so much about. Now, what is also possible, actually, what is also possible is that instead of having simply a mean like that, you can have also some combination, because here either you say min and then all the followers are friends, or min max and then all of the followers are enemies. But you can also have some combination. Some of them are friends, some of them are enemies in a sense, which means that now you reach a more complex situation, especially if your theta and all the functions are not linear. Then the situation can be a bit tricky to handle with. So all that is open question. I mean, this is food for the young people here listening to this talk. If they like this, then they can go that, and there are plenty of open space to develop, to my opinion. I mean, this is my opinion, interesting things. Let us go now to what is a classical formulation. I already said, so I would like to make some advertisement about this short state-of-the-art in multi-leader follower games that we wrote with Anton Svensson in the excellent book by Dempe and Zemko. So if you are interested in this setting where you have a classical Nash or generalized Nash, if you want, then go to this book. You will find plenty of things. In our chapter concerning several followers, but in the other chapters concerning one follower and plenty of very interesting things. Or of course, you can go to the excellent book that will soon be published by Martin, Ivana, and Martin, I forgot. Anyway, so the excellent book that which will appear very soon on bilevel optimization. And if you want to have a look to how to compute the solution of a single leader multi-follower where you have a Nash game at the follower level, then you can, for example, have a look to this tutorial that we produced 1 year ago with Martin. It's a very large method to solve single leader multi-follower as soon as your constraints at the follower level are linear. Then you can use this method. It is without big M. It is very easy to compute, and actually, even in this paper, we give it's kind of tutorial. We give some codes to solve these single leader multi-follower games. So do not hesitate to use it. Right, but now I will change and I will forget about Nash. So the idea is now that I would like to forget about the fact that we have a Nash to model the interaction between the followers. And one possibility, especially if you have some uncertainties, is the Ranner approach. So I will briefly speak about existence and application to industrial ecoparks. So imagine that you have still a structure like that, but here, this interaction here is no longer, you have some uncertainty here, some kind of omega, if you want, somewhere. So of course you can have an approach of chance constraint at the follower level, or you can have stochastic approaches with expectation in the objective function, things like that. The concept of Ranner is a bit different. It has been created by Roy Ranner in the 60s, and it is intrinsically taking into account the possibilities that the world will change. So essentially what we want to deal with is a single leader, well, optimistic, single leader Ranner follower, which means that the player, the followers, they will interact in a Ranner to find a Ranner equilibrium. So I have to describe what is a Ranner equilibrium, but essentially it is a Nash game with uncertainties. How does it work? Well, essentially, so you can have a look to this paper, for example, where we presented this kind of Ranner things. How does it work? Well, you have a set of players, you have one leader and several followers, and they interact in a non-cooperative way. But the difference with Nash is that you have actually time. So you have the game starting at time 0, and then some evolution of a finite numbers of iterations. Say you have t equals 0 and t equals 1 to simplify. Okay? And then what happens is that when you actually decide, when you sign the contract, this is at time 0. But you don't know the state of the world at time 1. Possibly it will be extremely sunny, it will be raining, economy will be good, economy will be bad, whatever. And so you have a set of scenarios. So the approach of Ranner is based on scenarios. So you have scenarios, and of course, if you have several steps, then you have a tree. Using the term of contingency. And so what's happened is that the leader have a state contingency vector, right? And the followers, actually, there are some resources, some kind of goods, if you want. And what's happened is that you have something here. It is the state of the art. This is the state of the world, the state of the world at iteration t, at time t, if you want. So everything of that depends on the state of the world, as you understood from the tree. And so I will not detail everything of that. You can have a look to the paper, but essentially what's happened is that the leader will have to make a decision, and it is optimistic, so it will be decision of leader and decision of follower, so X and Y here. And you have some endowment, initial endowment that you have here, and you have some vector of state contingent vector. right? And which are kind of percentage of the goods. You look at that here, represent the percentage of the goods that you will use at time t for good H. And you are playing I. But it depends, of course, of the state of the world at time t, and there are several scenarios, right? And going further, blah blah blah. So we have the decision of the followers. We have forward markets and also contingent prices, which will be decided depending of the state of the world. And finally, you have forward contracts that you sign at time zero. So you sign them at time zero, and they will be executed at time 1, or 2 and 3, and so on. And finally, the definition of runner from his paper of 60, I think it is 65 or something like that. Then a big vector of plan, prices, price expectation, and so on is a runner equilibrium if what? If you have a look to the 3 here, what is this? This is more or less a Nash. But actually you have another step, and this step is a kind of clearing. So you have a kind of Nash and there is a clearing. And this is, of course, for any possible state of the world, right? Sometimes it is called also Bayesian approach with incomplete information. And then, so what's happened is that then what we are looking for is we are looking for this bi-level optimization in which a leader takes decision X, knowing that the rest of the variable will be runner equilibrium, depending of X and thus also the state of the world. The Fi are quasi-concave and continuous, that the Fi are strictly increasing in the trade and consumption of the variable, which means this also here. And yeah, that's kind of classification. And how can we prove existence for that? Well, the first step is to reformulate a runner equilibrium into what? Into a quasi-variational inequality. So this is the main tool here that we use. We reformulate, that is, if and only if we have a runner equilibrium, if and only if we have a quasi-variational inequality. Wow, that's very good, because then there are several existence for quasi-variational inequality, stability, results for quasi-variational inequalities. Okay, takeaway. Let's go to the takeaway. So what is the takeaway here in this talk? The idea was actually in single leader and multi-follower, you can, or you should, or you must consider different type of interaction between the followers. That can be uncertainties, so the runner. That can be the strong equilibrium coming from Oman. That can be, and I didn't discuss this, the non-self constraint map, which is extremely useful for electricity market. That can be also local Nash equilibrium instead of global, because global is really too much. Or that can be even the fact that you don't have utility function, you just have preferences. So the idea is essentially to open the mind and to say, well, okay, classical things are single leader, multi-follower, but you can consider different kind of equilibrium at the lower level and deal with and do a lot of things with that, computation, existence, stability, this kind of thing. And this is just, I would say, a list of what I did with my co-authors, but I encourage you to consider other kind of equilibrium or the kind of interaction between the followers. And why to do that? Okay, just for fun, for math, of course, but not only, because then, thanks to those different interaction, you will tackle different applications, in particular in energy, but not only, in many interaction between the followers and single leader followers. You have different constraints, different approaches, and those different kind of equilibrium at the lower level can be of definitely different kinds. And don't hesitate to consider that. This is full of open questions and this is full of potential applications. So this is the takeaway of my talk.